Welcome to Georgia Tech Manufacturing Institute's Lunch and Learn lecture series. My name is Dr. Butler Brown. I'm a senior research faculty education and workforce development director. GTMI. Before I introduce today's speaker, I'm just going to introduce GTMI and give some brief instructions for the audience. GTMI is one of several Georgia Tech interdisciplinary research institutes that focuses on manufacturing development and employment. GTMI's mission is to identify, scale up, and integrate critical technologies for emerging advanced manufacturing sectors. GTMI has a wide variety of equipment located on main campus for basic research, as well as nearby on 14th Street in our Advanced Manufacturing Pilot Facility, or AMPF. GTMI's AMPF is the headquarters for the Georgia Artificial Intelligence and Manufacturing, or Georgia AIM project, worth $65 million. Funded by the Department of Commerce Economic Development Administration. Georgia AIM is expected to profoundly impact Georgia and the nation's economy through the equitable development and deployment of talent and innovation in artificial intelligence for all manufacturing sectors. The AMPF has state-of-the-art equipment in metal additive and hybrid manufacturing and is transforming into a demonstration facility for automated smart factories that incorporate industrial IoT, AI, digital, and robotic manufacturing technologies. The AMPF is also home to GTMI's Manufacturing 4.0 Consortium, with over 30 industry partners and growing. All right, so GTMI hosts a Lunch and Learn lecture every semester. And this is actually our 6th lecture together, and we're, for the spring semester, we're in person, and we're also streaming online via Zoom. These sessions are excellent opportunities. Georgia Tech faculty, undergraduate, graduate level students and researchers from the global manufacturing community to learn and share advanced manufacturing knowledge. All right, so we want these seminars to be interactive. So if you have any questions, please raise your hand, or if you're online and you have questions, please put them in the chat and we will address them immediately or at the end of the presentation during the Q&A session. All right, today I'm pleased to introduce Dr. Mohsen Moghaddam, who will discuss intelligent XR for adaptive task guidance in future factories. Dr. Mohsen Moghaddam is the Gary C. Butler Family Associate Professor in the H. Milton Stewart School of Industrial and Systems Engineering and the George W. Woodruff School of Mechanical Engineering here at Georgia Tech. His research focuses on developing human-centered computational models, algorithms, and tools at the intersection of AI and spatial computing to enhance learning and creativity in various industrial use cases. Previously, he was an assistant professor in the Department of Mechanical and Industrial Engineering at Northeastern University in Boston. And Dr. Moghaddam earned his PhD in industrial engineering from Purdue University, completed a postdoctoral associate position at GE Purdue Partnership in Research and Innovation in Advanced Manufacturing. His research has been supported by NSF, DARPA, the US Navy, and industrial firms. All right, today's presentation will discuss ideas to transform XR, or extended reality, into intelligent companions for future workers that accelerate their progression from novice to expert in performing complex psychomotor tasks through adaptive interventions tailored to their individual needs, skills, and knowledge. An intelligent XR framework will be introduced designed to facilitate such adaptive interventions through multimodal data-driven activity, understanding, error detection, prevention, expertise modeling, and the generation of personalized instruction. So Dr. Moghaddam will highlight example use cases in mechanical assembly, precision inspection, and human-robot machine interaction. Dr. Moghaddam. Thank you.
Well, thanks, Wade, for the very kind introduction and for the opportunity to present our work here at the GTMI Launch and Learn series. I'm going to time myself. Hello, everyone. Thanks for sharing your lunchtime with me. I have about like 45 minutes worth of presentation, but if in the middle of the presentation, if you have any questions, feel free to unmute yourself for Zoom participants or like in the room, raise your hand and ask any questions you might have. All of us have had like a few people at least in our lives who have taught us some sort of skills. From riding a bike to learning like an instrument, for example, driving a car to swimming and so on and so forth. And assuming that they were successful in doing so, in all of these cases, they provided their support in such a way that we do not fail, we do not give up, and we gradually learn and develop that skill without being overly dependent on them, and gradually become independent enough to continue on and learn that skill and kind of like master that. And there is evidence that shows that this whole process of skill acquisition generalizes to any skill-based task. That at the beginning you start with the procedural training and procedural knowledge, and gradually that procedural knowledge turns into what we call declarative knowledge. That you go beyond knowing what to do to understanding why that is important to be done. What are other alternative ways to do that, and then be able to address unexpected scenarios and situations that happen as you perform the task. Now imagine having an expert trainer who knows it all in all procedural tasks related to manufacturing, or at least in one specific use case. And then imagine being able to clone that person infinitely, have multiple copies of that person, then make them a miniature version of themselves, and then put them over the shoulder of every single factory worker. And they constantly look over their shoulder, provide the instructions to them that is tailored to the context of the task and what it performs. So, well, that's the vision of what we're trying to accomplish in our project. Obviously not to clone people, but to create what we call intelligent companions and assistants for those factory workers during training, on the job, and also during task performance and execution. Well, then one might ask, why is that important? So because all of us, most of us, the ones who have been in the manufacturing domain doing research and our stakeholders, know that for a very long time, for decades, the vision was to materialize a lights out factory. This is a code that is decades old. And the idea has been mostly to find a way to replace people with machines, with automation, and for good reasons, because people are not as predictable as machines, and there's always shortage of work, right? But we all know that this future has not arrived yet. We know that it is impossible to fully automate, at least right now, maybe in the near future, yes. And that's because as we create more advanced automation technology, there's need for not only for less people, not necessarily for less people, but for people who are skilled with more complex and cognitively demanding tasks. So the vision is that what if we, instead of trying to focus, or in addition to trying to focus on automating most of the manufacturing processes, if not all of them, what if we also focus on unlocking the cognitive and physical potentials of these workers, and trying to think about how do we blend people into the manufacturing process rather than finding ways to replace them with machines? And that has been, like automation has been mostly Industry 3.0, even Industry 4.0, but now we also hear about Industry 5.0 that I did not know it actually existed until I visited Europe this summer, and notice that it has actually been officially announced by the European Commission that like one of the main pillars of Industry 5.0 is human-centered automation. So, and that is also backed by data that these numbers have been changing, but these numbers have been changing over the past few years, but there's still, this is based on an article by Deloitte in 2024, that shows that there's still a projection of almost 2 million jobs that will remain unfilled until over the next decade, like until 2033, I believe. And out of all different contributors to that, you see that a major contributor to this skills gap, this lack of enough skilled workers, is retirement. But in addition to that, we know that there's introduction of new technology. Of course, baby boomers retiring, the new generation is not interested in manufacturing. And another major pain point and issue here is that there is not there's a lack of consistent training. And you see that the skills are now being shifted to what we call psychomotor skills, cognitive skills that are at the intersection of problem solving, decision making, and also performing complex tasks. The most rapidly growing example of that is simulation software, digital twin, 3D, real-time 3D virtual prototyping, to also like manufacturing, machining, critical thinking, and so on and so forth. So our vision is to try to think about how do we leverage new technology, AI, specifically in our case, AI, extended reality, and robotics, to augment people, to unlock some of their potential, to lower barriers for people with different abilities, both cognitive and physical, to be able to join the manufacturing workforce and become an active participant. Because we believe that there are millions of jobs that are expected to remain unfilled over the next decade, but there are also, I suppose, many people, if not millions of people, who will need those jobs. But the problem is that skill mismatch and lack of technologies to accelerate their training and to kind of like help them join the manufacturing workforce. So I have listed here IEEE case. We are I'm hosting a session this year at IEEE case that focuses on this overarching problem. How can we augment people with different abilities, cognitive and physical, who could have disabilities or like different types of abilities to be able to join the manufacturing workforce. So within this domain, under this overarching umbrella problem and vision, what we have been focused on mostly is extended reality and AI, what we call data-driven extended reality, for task guidance, assistance, and industrial training. Those of you who are familiar with AR and VR and XR might be a little bit confused with all of these terminologies, and there's still not a consensus, but in case you are not familiar with AR and VR, there's an entire spectrum from fully immersive training all the way to augmented reality, where you bring the information to the job, on the machine, on the task, and so on, and provide it to the person as they perform the physical task. And there is evidence that shows that XR in general, from virtual reality training all the way to augmented reality training, can be effective in enhancing spatial reasoning and scaling training, because in the case of VR, you have remote people who may not have access to the equipment to be able to go through the training and get ready for on-the-job training. In the case of augmented reality, you can provide instructions to them on the job, where it's needed and when it's needed. This is an example of a project that we did for the US Navy a couple of years ago. By the way, all of these applications that I show you are ready to demo. If you are interested and you want to come and take a look or go through the experience, our lab is in right by me. And we have all the setups ready to show you as well. So in this case, you see in the case of virtual reality, you immerse the user in the training environment, you provide them kind of like contextualized information as they go through this virtual reality game. For example, in this case, it's a cold spray additive manufacturing for maintenance and sustainment operations done by the US Navy. That was a NAVSEA project, where we walked the person through the process of preparing the cold spray machine. This is another example of the robotic painting in Warner Robins facility here down in Georgia, Air Force Base, where the task was to train their technicians who used to do painting manually to learn how to operate a FANUC robot in their new robotic painting environment. So anyways, in a nutshell, AR and VR have different affordances. VR can help you immerse the person in the training environment in 3D, which compared to videos or compared to 3D animations on the screen, has some advantages in terms of spatial reasoning and retention. And augmented reality, of course, can be used for training and also after your initial training on the job. So what we have been trying to address is that these devices, first of all, like this training system that I showed you, there is still something lacking in that example of the expert looking over your shoulder to provide instruction. And that element that is lacking is that all of these instructions are one size fits all. You provide, it's like an immersive PowerPoint that you go through the training, you have to navigate through step one, step two, step three. It doesn't tailor to you and what you need as the user. So that is the whole idea behind this intelligent XR framework that we are talking about. And the good news is that these devices can be used as an input-output device, meaning that you can provide the instructions in AR or VR to the person, but at the same time, you can use the headset, different sensors on the headset to capture different modalities of data, like hand tracking, gaze tracking, your egocentric RGB, environment depth, and so on, and even some physiological signals in some advanced VR devices. So the question here is, how can we use this data in real time to make these interventions more contextually aware, to make these interventions, these training systems in augmented reality, for example, tailor to what the person needs at that moment in time, based on their level of training, based on based on the state of the work, and based on even some cognitive states. So we ran an experiment, a Wizard of Oz study, 2 years ago or so, where we created 3 different versions of an augmented reality training system for inspection. So in this case, we had animations, we had videos, we had instructions, step-by-step instructions, and we had 3 different versions, 3 different conditions of it. Full interventions, which was, again, like the example of that immersive PowerPoint, that you had to go through a series of steps to prepare the gauge, calibrate the gauge, do the inspection, and then do the readings and so on, and then make a decision whether to accept or reject a part or its characteristics. We had another one that was on demand. So we instructed the users, the participants, to only consult with the information if they needed help. Otherwise, try to rely on your own knowledge. And we also had the adaptive intervention, system, where we had a Wizard of Oz system. We had a script that in real time turned interventions made by our students into an AI sounding intervention for the user. So the user did not know, the participant did not know that this is a human. It sounded like AI. And the interventions only happened when they made an error or when they were stuck or confused. And we generated that intervention at that very moment. So the results of our experiments showed that the most important aspect, the most important finding was that it improved task performance, learning, and also knowledge transfer between different inspection tasks. So in a nutshell, the message here is that adaptive interventions not only help you perform the task or go through the training more efficiently, it also helps with learning and also knowledge transfer. So this is the Intelligent XR framework. That is the main theme of this talk from this point on. So the idea here is that, as I already mentioned, is that how can we turn head-mounted augmented reality or even virtual reality, but our focus is mostly on augmented reality and on-the-job training and task guidance. So the main question is that how can we turn this into an intelligent companion for the worker? During training and on-the-job training, and also assuming that hardware will eventually catch up, and we have these, we have lightweight curved glasses that will function as like Microsoft HoloLens, that's very bulky and you cannot wear it for more than 10 minutes. How can we turn that into an immersive version of a guide, an assistant that constantly looks over your shoulder, has a good understanding of the context, and what we mean by context is what is happening on the outside, the state of the task, and also what is happening inside, the state of the user's cognitive state, and also the interaction between the user and the machines in the environment, assuming that we have like human-robot interaction scenario or human-machine interaction scenario, and I have some examples to show you. And then based on all of this contextual information, generate the content that is needed at that very moment in time in different modalities. It could be from at the very basic level, the most basic level is text. You can imagine an immersive version of GPT, but an immersive version of GPT that has contextual understanding about what has happened and what state you're in right now in terms of your cognitive state and also the state. And provide interventions, different modalities from dialogue all the way to spatial visualizations that kind of like pop up and appear as you go through the task, and then stay out of the way if that is not necessary. Okay, so from this point on, I'm going to spend a couple of minutes on each of these 4 boxes, and I have some examples of technical work. That if you have any questions about those, by the way, feel free to raise your hand. I also have cited the papers related to each of those. But I'm going to spend some time talking about each of these examples. First, I'm going to talk about activity understanding. And what we mean here is that, in a nutshell, given the data that we can capture from the headset, could be egocentric data, could also be exocentric data that we can capture from external devices. Understand what I'm doing, what I've done so far, what I'm doing right now, and what step of the task is happening, and at like different levels of granular step and all. This is an example of a project that we did a while back, where we used hand escalated data that we can capture from Microsoft HoloLens. It gives you 26 joints of, and each of them 60 pose, translation and rotation. And the idea was that, given this real-time data that we can capture from the headset, how can we detect in real time? This is all happening in real time, and you see the debug window behind here to show the capability of the system. Detect what actions the person is performing, what action the person is performing at that very in real time. So in this case, we trained a temporal graph network, which is TGN, which is a combination of graph convolutional network and temporal convolutional networks, which in a nutshell captures the spatial and temporal features of your hand movement data in real time. And based on that, we can label in each frame what action the person is performing, for example, pressing, holding, sliding, and so on. This is a work in progress. We have reached a pretty good performance in terms of accuracy and also in terms of our frame rate, but we did not consider background frames in this case. So right now we are working on an extension of this work because the majority of time is spent on not necessarily performing something meaningful. So this is a work in progress, but at a very high level, the idea is that how can we detect the activities performed by the person as by the operator as they go through the task and perform different activities, in this case for precision inspection. Now, this could potentially combine with different IoT data that we can capture from the devices, from the environment, help us detect not only the hand actions, but at a relatively higher level, the step, and also detect errors of omission, errors that are related to forgetting, for example. We have, let's say in this case, we have an inspection task where I have to go through these steps down here, where I first have to identify, assuming that this is a procedural task, a strictly procedural task, or it could be like a linear task, or you could have like different orders of performing. But there is some precedence between different steps. Like you have to locate the caliper, you have to turn it on, switch it to inch mode if it's not in inch mode, and so on, and then first clean it and then calibrate it and start doing the inspection, right? So speaking of contextual data, and now let me see if I can zoom back. Speaking of using contextual data, the hand action detection model that I just explained to you provides one piece of the puzzle. Like in this case, using the RGB and depth data, using the depth data, I can keep track of the hand activity of the person. But we also put small IMUs in the part that detect the movement of the part. The gauge also had an IMU sensor and also the reading was a digital gauge, and all of them were connected to a server that would, like in real time, keep track of the hand activity, movement of the part, the gauge, and also movement of the gauge, and also the reading, the inspection values of the gauge. And collectively, we created, in this case, a rule-based system. I understand that rule-based systems are not hot anymore, but at least it works. And the extended version of this could potentially be a system that is not rule-based, completely data-driven. But the example that I have here to show you is that you see that the gauge is on right now in this interface. Again, this is just to debug. So in this interface, as soon as the person locates the gauge, this turns on. So we have some completion criteria for each of the steps that help us detect where the person is, what has been accomplished, and considering the task model, the task graph, tell us whether they have, for example, in this case, first of all, where they are in the task and whether they have forgotten anything. So in this case, they locate the gauge. As soon as you press the button, and also it also reads the hand action. As soon as you press the button and something changes, it switches to inch mode. And in this case, intentionally, the student skips the wipe cleaning step, which is that hand action that was not detected by the system, and tries to calibrate the gauge. And the system throws an error and says that, hey, you forgot to calibrate the gauge. You forgot to wipe clean the gauge before calibrating. And then as soon as it detects that you have opened it and wipe cleaned the gauge, it clears that error and allows you to move forward. So this is an example, again, like to, in the interest of time, this is an example that shows us that using these different modalities of data, we can create systems that keep track of hand movement, the steps, errors related to that, and also maybe errors related to poor technique or incorrect technique. And collectively, they help us create at least a partial better understanding of the context of the system in terms of the activities that have been performed so far and the activities that are being performed right now at this point. So our intelligent companion has one bigger piece of the puzzle, which is the activities that are happening on the outside. Now, the other thing that we need to keep into take into consideration is understanding the user. Yes.
So is it predicting an action for every frame? It looked like the predicted action was fluctuating.
Yes. In that case, it was per frame, but that's like the finest level of granularity that you can do. But the idea here is that another open problem in computer vision in general is egocentric step detection. So step detection is that you need to look for the completion criteria for that particular step, right? But even like detecting hand actions could be useful, because in this case, we can create logic that would help us detect errors, for example. I did not detect anything related to wipe cleaning the gauge, and I have a sign of you trying to calibrate the gauge, but you have not wipe cleaned it, right? So in real time, the system can also detect the errors, right? But that's a very good question. So that's a higher level of, I have an example of that in the upcoming slides, like the fine grain and more like coarse grain and action labels. So the second part is understanding the user. Now that you have a good understanding of what is happening on the outside. Now let's think about what's happening on the inside. And we have focused on two examples of this, understanding how good the person is in terms of technical efficiency, like based on, again, in a completely data-driven way, given, for example, the gaze data and hand data and everything that you can capture from the headset or maybe other devices. Can you estimate how good the person is? Because another thing that little expert needs is like, if you're good, I should stay out of the way. If you're struggling, if I notice some signs of novice behavior, maybe I should provide more scaffolding, less scaffolding. So that's another idea about this intelligent XR system. This is a project that we did for DARPA, the PTG program, Perceptually Enabled Task Guidance. The example here was unfortunately cooking, but we can generalize this to other, like more manufacturing related domains. For example, in this case, the idea was that can we estimate the expertise of the user based on their gaze behavior. So what we did was that, in this case, we used an add-on, but we could also use HoloLens's egocentric camera. So given the RGB frames, we can do object detection, right? And we can also, for each frame, we have the gaze coordinate, right? So given the gaze coordinate and object detection in real time, we can keep track of the visual attention of the person. Now, the idea here is that as you go through the task, performing the task, depending on where you are, now step detection becomes important. Depending on which step of the task is happening, some of those items that you see on the table become relevant AOIs, relevant areas of interest, and some other items become irrelevant areas of interest, right? For example, if I'm in step 4, and in step 4, I need that, I don't know, filter and the cup, right? So those become relevant AOIs, but they're also irrelevant AOIs, right? And now based on my gaze behavior during that step, you can tell how familiar I am with the task, right? So if I'm spending too much time fixating on stuff that are not relevant or should not be part of my attention at that point, right? So the system can estimate how good I am, right? The idea here is that experts, and then our results also showed, again, this is another work in progress. We presented this at ISMAR, but we need to work on the extended version of that. And the student who did this research is sitting in the audience. So, but what our preliminary results that we presented at ISMAR showed that experts tend to like fixate longer on relevant AOIs and have less frequent saccades. So they have more stable visual attention behavior compared to novices, but that still is to be further proven or disproven. So, but the idea is that if you are familiar, if you are good at performing something, you should be familiar with the tools and the items that you need to perform that task, right? And if you spend too much time scanning, looking at items, or if the environment looks so novel to you, and there are things that you're trying to understand what they are, that maybe is a sign that you need help, or that maybe is a sign that you don't know what needs to be done. So this was about expertise estimation just using gaze data. Then the next question we asked was that this may not necessarily be, this is not a comprehensive perspective because expertise, there are other dimensions. Like a good example that we've been using to kind of like pitch this idea is that in an operating room, we have the surgeon and surgical assistant. Both of them, if assuming that they're a good surgeon and surgical assistant, should have similar gaze behavior because both of them should be familiar with the items that are needed to perform the surgery, right? But the assistant may not have the dexterity of the surgeon. They may not know how to do the suturing, how to perform the operation. They may not have the knowledge of that, right? So there are other metrics, other dimensions to be considered. So what we did was that we went back to our ear inspection use case. And in this case, we set up an experiment where we brought expert and novice participants to the lab. And we first trained both of them in the first module, which had like 3 inspection tasks. And then the second one involved, the second session, which was actually the test and data collection session, involved the task of, okay, given these 3 parts, these 3 characteristics, your task is to identify the right gauge and then use that gauge properly and tell us whether this is a good or bad part. And then we collected different modalities of data from them, including gaze, but also some self-reported data, some quizzes that we had in the system, and also their hand movement, for example. And then analyze the data afterwards to see if we can identify patterns in expert and novice behavior. And this is a paper that we're hoping to be accepted. We have already done 1 round of revision for IEEE TSMC. Some of the findings from that paper are that, first of all, we identified that in some aspects, there's not much difference between novice and expert behavior, but the metrics that turned out to be significantly different were visual scanning, the effect of their prior experience on performing the task, some of the NASA task load index TLX reports in terms of performance, perceived performance, and frustration, and also the speed and smoothness of their hand movement. So visual scanning is more about gaze. This is more about hands. So and then we also ran some correlation analysis to see if there are any correlations between different metrics that we measured through this. And this matrix shows that at the first glance, there's not much, there's no strong, except for like the hand speed and hand movement, there's no like significantly strong correlation between these different metrics that turn out to be significant in like comparing novice and expert behavior, telling us that there are still like there are indeed multiple dimensions of expertise. And for example, one of the like previous experience and also perceived performance, we found it to be almost like strongly correlated. And another interesting finding was that visual scanning and all of these hand speed and smoothness data showed very negligible correlation, meaning that, again, the same example of surgeon and surgical assistant, gaze behavior and hand movement are not necessarily correlated. Another interesting finding was that in this case, in this paper, we tried to come up with a theory not a theory, like a theoretical framing of different dimensions of expertise into cognitive. And we ran a PCA analysis, and the analysis showed that in terms of the two main principal components, visual scanning, prior experience, and NASO-TLX, mostly the cognitive stuff contributed to one of the principal components. And the physical metrics like hand speed, movement, and help seeking in the form of pushing the buttons in AR and so on contributed to the physical. Again, these are very early and very still, I would say, immature findings. But the idea here is that we could potentially consider categorizing these different dimensions into cognitive and physical so that we can have a more comprehensive understanding of their performance. And also the findings showed that if we come up with an overall ranking of experts and novice based on these PCA findings and these metrics, experts tend to be ranked. There are some outliers. There's novice here that is self-identified novice, but in general, this could potentially be the beginning of a new line of research on expertise estimation based on multiple modality data that eventually will serve us in the case of AR training and task guidance. Another very quick example, again, I have all of these citations here, by the way. If you have any questions after this, I'm happy to stick around and answer questions. This is another example of an experiment that we ran and presented last year at ISMAR, where in the case of cold spray additive manufacturing, the VR system that I showed you, we captured gaze data and pupillometry, so pupil dilation specifically and fixation duration, and used them as predictive features for cognitive load. In this case, we had cognitive load labels based on NASO-TLX mental demand. So low was considered no cognitive load, and high was considered yes cognitive load. And we used the 2000 sliding window to essentially like feed those sliding window data of pupil dilation and fixation, and trained different machine learning models, nothing fancy or super complicated, but even we identified that even using an MOP or random forest, we can get reasonable performance. Again, this is another ongoing line of research, but the idea is that can we use, just based on gaze and pupillometry data, if we can also throw in some other physiological signals or even like EEG, that could give us better performance. But can we use these like cheap and accessible data, available data, without being too intrusive to estimate how cognitively overloaded the person is. But again, going back to the big picture, now our intelligent companion has more contextual information about not only the task, which was activity understanding, but also the state of the user. I'm gonna now briefly talk about the third one, which is interaction with machines. Because like in most of these tasks that I showed you, we do not have, all the examples that I've showed so far are manual tasks. But we also have another, what if there is a robot involved? What if there is interaction with the machine? This is an example of a setup that we have in the lab right now. If you are interested, you're welcome to test this. Unfortunately, this is an extended version of a prior work that we presented at ISMAR. So in this case, the idea is to turn augmented reality into a how do you say it? Like a medium between human and the robot. So augmented to communicate intent bidirectionally. So the human in this case, we have this AR training system. So it's an assistance system. So we have the instructions, we have the guidance that if you need that part, it shows you what parts you need in order to perform this part of the task. So if you look at that part and dwell on it for like 2 seconds, then the robot will pick up that visual attention data in this 3D environment and gives you that preview. The ghost of the robot kind of like leaves the body and shows you that, okay, this is what I'm gonna do next, right? You have 2 seconds to change your mind, 3 seconds to change your mind. Otherwise, I'm gonna hand you the part or I'm gonna execute the task, right? And so this is an extended version of everything that I've talked to you so far. In that, you still provide contextual information, instructions to the user, but also use this interface as a way for the user and for the user, for the human to interact with the machines in the environment. So this was an example of the human-robot interaction, and then everything else that I've talked to so far is applicable here. Step detection, error detection, cognitive load detection, using other modalities of data to estimate the cognitive state of the user and so on. So, and again, like if you're interested, we're happy to talk more about this system, and you're welcome to even volunteer as a participant if you're looking for research. And some of the preliminary findings showed that in the case of having this interface compared to no visual feedback from the robot, again, I'm going to quickly skim through this. We have that would improve completion time, task accuracy, because it provides you with the information that you need to perform the task. But I would say the most important finding, in my opinion, is the confidence and trust, because by providing the contextual information, especially the robot feedback to the user, you kind of like lower the fear of, okay, I don't know what this machine is going to do, and then creating more transparency for the user as they interact. And the other example that we've implemented at Northeastern University at the Cyber Physical Factory is an example of combining IoT data with augmented reality to turn AR into an immersive interface for the user. I'm happy to talk more about this. Is a little bit tangential. It's not directly related to that framework, but it is possible to turn augmented reality into a system that not only captures data from the user, but also from the machine. So in this case, we created a pipeline through PTC's Kepler, ThingWorks, and Vuforia, so that in real time you can stream data from the machines, from the PLC to AR, so that you visualize real-time data to the user, and also turn that interface into also a control interface, an immersive HMI, so that you can control the machine in real time. So there's bidirectional messaging between the user and AR and the system. And in this case, we have very simple toy examples of like having buttons that show the status of the machine, and also so that, for example, in this case, the gripper is open, the arm is down. So as soon as you click on that, you unlock, you unclamp it. Now it visually gives you the feedback that, and this all happens in near real time, that sometimes the buttons don't work, but like in general, the idea here was that can we extend this idea beyond just the data that we can capture from the headset, and also bring in the data that we can capture from machines. So I'm gonna skip this, but you have this, it's being recorded, happy to talk about this, but in general, we found out that the spatial HMI is much more effective than the screen-based HMI for multiple reasons. This was presented at ISMAR, and there's a paper, I'm happy to share that with you. The last piece, last but not least, the other student who did this research is also sitting in the audience. So the last piece is that how can we use this contextual data, the inferences that we can get from different modalities, and create a system that makes interventions based on that contextual data that we can get from these different modalities, different boxes. So the overarching idea in a nutshell, if I were to just quickly summarize it, you can imagine now an immersive version of ChatGPT that, for example, when you have, as you go through the task and perform the task, let's say you have a question, right? You're stuck somewhere, right? Or you need help, or maybe you don't even say anything, the system intervenes, right? But when if you ask that from ChatGPT, it tries its best to answer the question, right? For example, I'm stuck, I don't know what this button is for, I'm getting this error on my HMI and so on, right? But the idea is that can we also bring in some other modalities of data that, like some of these inferences, like step detection, the user state, and so on, and the data that we can capture from the headset to help that LLM answer questions more effectively, right? And this is not a published work, so I'm just showing a very brief preview of this. that we are testing this on a data set that is published by Microsoft Research. There's a platform that would allow you to capture these data in real time. You see that there's this example of, again, hand action detection, very fine-grained hand action detection. And the idea is that can we use this contextual data in addition to in addition to the question, for example, that is asked by the user to help the system answer the question. And our preliminary experiments, that's all I can share at this point. How we're doing it, I'm not going to share it, so don't worry about it. But the idea is that based on some preliminary experiments, we noticed that even GPT-01 cannot answer some of these questions that our system is capable of answering. So we have in our HoloAssist data set, they have annotations of an expert in the room making interventions and answering questions. In this case, for example, the question is like the person is trying to set up a GoPro camera and they say, do I change that? And that's it, right? So yes, the answer, the ground truth answer provided by the human expert is yes, change the SD card. And we noticed that because GPT, there is nothing wrong with GPT, it's just a lack of contextual data. So if you provide more additional contextual information, it is capable of answering that question. So we are in the process of finishing this up, and hopefully this is a motivation to speed things up. Anyways, just to recap, so far I talked about intelligent companions, and just to kind of like zoom out and talk about that more like the bigger picture idea. What I would like to, as a lab, as a group, even as a community, there's like increasing interest, growing interest in the XR community and also in the manufacturing community, to kind of like shift the focus a little bit away from, there's nothing wrong with automation, but I personally believe that instead of automating, or in addition to focusing on automating things that basically automation means replacing what the human does with what the machine can do, right? What if we think about tapping into the potentials of people and some of the unique abilities of people that may not necessarily be, first of all, are hard to automate, and second, could potentially unlock some new opportunities for the company. Like, what if that next big thing, next big deal, next groundbreaking idea is in the head of someone who can't even make it to the manufacturing workforce, is being considered to be replaced, I don't know, by some robot or by some machine and so on. So we all know that like over the course of history, technology grows. It's like a loop that, new technologies come and people adapt. New technology comes, people adapt. But the problem right now is that the rate of growth in technology has become so quick and so fast that it's very difficult for people to keep on. So the idea is that, first of all, how can we help people adapt faster? How can we, in addition to helping people adapt faster, can we even think about, by blending people in, maybe unlocking or uncovering some new problems that we haven't even been thinking about, right? I know some terms are not to be used in terms of, but like you can think about like differently abled individuals, right? So another line of research that we're thinking about is that how can we focus on problems? How can we address problems that would lower barriers for people with different cognitive or physical disabilities or different abilities to join the workforce? And what if we connect all of this together and think about integrating a system of, like taking a systems perspective? And what are the some of the implications for other contexts? We're talking about manufacturing, but everything we do is potentially generalizable to other industrial domains. And lastly, I would like to leave you with some questions. There's a lot of text and we have like 2 minutes left or less. So, but in general, the idea is that how can we enable seamless real-time multi-model sensing and modeling of different human abilities, understanding the human at a cognitive level and physical level in this context of a system better. And how can we make this a bi-directional learning that not only provide contextually aware augmentation systems to help people, but also use the human data to improve the system. And of course, trust, safety, we're talking about keeping track of the person's gaze and hand behavior all the time, right? So there's privacy issues, there are trust issues that we should think about as we address these problems. And overall, error detection, and that is another very important problem that we haven't even, in our case, in our lab, at least we haven't, in this context, we haven't really done much work in that space. And what are the long-term impacts of integrating these systems, assuming that we'll eventually be successful in terms of the evolution, on-the-job training, and also independence or dependence on the technology, because all of this started for me, at least, by talking about Google Maps, that I could not drive without my Google Maps navigation, right? Because I'm just too dependent on that thing. Like I used to drive in Boston for like 2 years, but I told my colleague that, without my phone, I'm lost, right? After 2 years of driving here. So how can we also carefully design these technologies to make people not too dependent on it? So the special session, I already mentioned that to you, and we're also organizing another special session in Informs this year, but again, to get the message across and learn more from the community, continue to work on this topic. And if you want to learn more about our lab, scan this QR code and this. Thank you so much.
Yeah, we have about 10 minutes left for our question and answer session. So.
I got a question. So in your example of using these calipers and micrometers, those are very hand, someone used them all of my life. We twist it and get a different measurement. Have you considered some feedback from the instrument? Because you said, to kind of consider the technique,
Yeah.
so the image gives you the technique, but I watched as the image, the caliper was not parallel to the surface that you were measuring. So that would give you a different measurement. So if you had feedback from the instrument to say, we're way out of range, right? Is there any consideration for that?
That's a great question. So first of all, that's the error of not omission, but like commission is called, like error of like you're performing the right thing, but in the wrong way, right? Your technique is bad, exactly what you said, right? We haven't really done much work in that space, but it is possible to stream. This is what we did actually here. So we can stream data from the device to the app and write a logic that says, I know that for this particular characteristic, this is the range, right? So if your reading is way off, maybe something is wrong. But no, that's to my knowledge, that's a problem that no one has.
So would this be a reinforcement with their consideration, the initial training first, and this is just reinforcing, or with the expectation is you just go live and?
Can you repeat that question?
With using this technology, is it reinforcing?
Yes.
What you've already learned, or is it taking the place of?
It is reinforcing. And the idea is
so
not.
They've already had some training.
The idea is not to replace classroom, but the idea is also that, when you are sitting in a classroom, you don't necessarily, that may not kind of like get ingrained in your memory, burned into your memory, compared to when you actually make the mistake and you're corrected. And that's the study, the Wizard of Oz study that I mentioned. That in this case, we noticed some retention, and retention was as a result of the fact that we first allowed the student to fail and then intervene and say, forgot something. You did something incorrectly. But you're making a very important point here. And I think the problem that this potential solution that comes to my mind is mostly computer vision. So if we can find a way to constantly keep track of the alignment of the gauge and the part in real time. And then we also are getting some data that the person is now actually measuring something, they're reading something, or they're pushing something, right? And if there's misalignment, the nice affordance of this technology is that you can immediately correct them. Right. So this may not necessarily just be limited to training. This could potentially in the future, assuming that HoloLens becomes a pair of glasses that we wear all the time, it can correct you on the job, right? It can remind you that, hey, you forgot something, you did something incorrect. Sure. I'm not sure if I answered that question.
You did. Yes. Yeah, speaking of your Google Maps, any of us that use cash and go to the store and hand them cash and say if it's like $1.75, you give them $2. And they don't know how to count backwards, because if they don't have it on their screen, it's very difficult for them to give you the correct change back. You have to tell them.
Yeah, I would just, add on to that. I mean, part of what we'll do is we'll say, hey, make 3 or 4 measurements with a micrometer so you can get a little bit of statistics on what's going on. And a lot of times the people on the shop will just hit the button 3 or 4 times and just sort of be it. So you could actually track to make sure they're doing it right. But then you could do all sorts of interesting stuff like, yeah, the idea is to look at statistically. So if you have a novice making those measurements, they're gonna have a bigger spread, bigger standard deviation, and as they get better, it should get tighter. So you could even, I mean, sort of following along here, number one, you could make sure they're measuring the right thing. Number two, you could really take a look at what their learning is and if they need some, some more training and so forth. Along those lines, how do you have a feel for how we move them towards, we're not watching to see if you make a mistake, but we're there to keep you from making a mistake. If you make an error, you measure the wrong thing, or you're not learning fast enough, or you're just not getting it, right? I'm making 10 measurements and they're all over the place. And you just need some more training here. How do we change that culture of I'm being watched and so forth to, yeah, this sort. And by the way, I agree. You gotta wear safety glasses in the plant anyway, so
Yes.
it's coming.
Well, that's a great question, Tom, and I'm not sure if I have a good answer to that question because we haven't really thought about the privacy implications of this yet. So right now we're at this stage of thinking, is it even possible to do all of these things that we would like to do? But yeah, totally agree that. And also in terms of interventions, another question, open question, mostly like an HCI question, and also HCI, it could be like interdisciplinary HCI and learning sciences, is that what is the best way to intervene, right? When is a good time to intervene and what is the best way to intervene? Do you show them to do it in a constructive way, so that it doesn't discourage them, so that it doesn't, so yeah, I don't have, that's a very good question. That, in my opinion, that's an open question, and if anyone else in the audience have a good answer to that. But yeah, that's all I can say. But we haven't thought about privacy yet. Yes.
Well, the technologies that you have here could certainly be adapted for different, regimes where I could see as an expert mechanic or something, situate, or a surgeon, your hand tracking motion technology would be very useful because when I'm working on my car, a lot of the time I'm trying to put a nut on a screw that I can't see. You could have your hand being tracked by a camera positioned in line of sight of the object you're trying to manipulate. And I would assume the same sort of thing would apply to surgery. Many times surgeons are trying to manipulate something out of visual sight. So you could have a simulation, right, in your headset showing you where your hand is as if the engine were transparent or the bone is transparent or something like that. So this could, in my view, would be very useful even to experts to reduce accidents and speed up operations and things of that nature.
Absolutely.
I guess that's more of a comment than a question. Do you think that would work?
Good question. Yes, I agree. Right. So yeah, that is a very another important point that.
Good comment, yeah.
Yeah.
You have a question?
So with, I guess, XR in general with the headsets, it seems like a lot of different sensors all kind of giving data all at the same time. Have you experienced like accumulating error over time, especially in like the broad like space, like the calibration of the hand measurements like slowly drift off over time, or is it constantly like recalibrating itself? Or do all the sensors like fact check each other and says, well, there's no way the hand could be here if the vision says it's here?
Oh, no, we haven't done that yet.
Okay.
But like everything we do is, so the question is, have we done any calibration to make sure that there's no drifting and the data, there's no latency between like.
Yeah, just like
Data
over time,
collection and
like,
inference,
does the
right?
data just like drift off some?
No, and in terms of like frame rate for hand, it's actually quite high. It's like 60 or something. Like it's with HoloLens, it is a quite high number, and we may actually need to downsample. That is not that is not an issue in terms of, but yeah, the latency could happen, and as a result of that, there could be, and you're right, I mean, looking at this video, I see that the alignment is not right. So, but this is also just to make a comment related to that, is that just an FYI that Meta is now investing a lot of money and effort into creating a next augmented, because HoloLens is discontinued. Magic Leap is another example of technology that can do that, as a see-through augmented reality. But the new headset is coming out of Meta, and there are 2 data sets at least that are looking into these egocentric multimodal data set, data that you can capture from the headsets. The HoloAssist data set that I mentioned was this data set that I mentioned was captured using HoloLens. There's another data set, Ego Exo4D, by Meta Aria glasses, that does the same thing, hand tracking, gaze tracking, and so on. So you will see more of this kind of research over the next couple of years. But no, in terms of latency, we haven't looked into that problem, but that's a very valid problem. Eventually, once we're ready to implement this in an actual AR system, we haven't reached that point yet.
Just to follow on to Clint's point, one super useful thing, I can tell you, most of the crashes I see with robots and machine tools is instead of being set at the, 1 millimeter, per click or 1 millimeter, per second range, it's up at 100 or 1,000, right? So for a rapid, and people get that wrong, and they just say go, they just hit the boot button and the thing just goes flying right into a wall, or it just crashes right into the chuck. Just actually seeing what the settings are independently of what they, seeing what the knob is set to before somebody spins that dial would actually be very useful. And I think it would avoid a lot of, I think many of us have probably experienced that, whether we're the ones that spin it or whether we're the recipients of the information that your machine just crashed. So I think there's some pretty easy and cool things that you can do to keep people from doing a lot of damage out there.
Yeah, I'm not sure if I have like 1 minute to also comment on what just Tom said, over time, but.
Go ahead, yeah.
Yes, so that's a very important point. And then I just showed an example of that. And in this case, there was nothing wrong with the button of the machine. By the way, we can create a real-time pipeline between the machine's IoT data and AR that in real time, you can also implement the logic that even reminds you that, hey, this is not supposed to be at that range, right? So in this case, we intentionally, for example, skip that white planing the surface, because this is like cascading failure. You forget to white plane, then you accept the bad part or reject the good part, and you cause trouble down the line, right? So the system, for example, in this case, can keep track of your performance and in real time tell you, hey, don't forget to white plane this, or hey, that knob doesn't sound right? So maybe you need to do something about it. So, and that is where the technology goes, I think, in my opinion, beyond just initial on-the-job training. Assuming that you have this safety glasses that you're wearing all the time, we could prevent lots of errors like that. But thanks for the great confidence. And I think we are over time now.
Yeah, we are.
So just one final, talking about the culture and the change. A lot of people like instant rewards, right? So maybe perhaps when you do something right, you get maybe a message flash across, great job, you did it right. Maybe it tracks the number of times that you do right. And maybe as an employer, there could be rewards for that in the future.
Yeah. Digital encouragement there.
Emojis.
Emojis, yes.
Yes. Well, thank you all so much. This has been an excellent presentation. I want to say this. Welcome to Georgia Tech. And
thanks.
Welcome to Atlanta. He's a new professor here, and he's got a research group with him. Some of them have come from Boston, Northeastern University. So welcome to Georgia Tech.
Welcome to my students, Steven, Parisa, Maya, Becky, who are sitting here in the audience.
All right, so we will have one more lecture for our series next week. It would be Professor Carolyn C. Prasad, who's going to talk about process innovations for polymer additive manufacturing. So we'll talk a little bit about some of the polymer additive techniques that we have in our facilities. Yeah, that's it. So we thank you so much for your attendance, and please come back for one more, and we'll be done with the spring semester. Thank you so much.